Welcome to all of you in the class of fluid mechanics and hydraulic machines. Today we are going to discuss about the energy losses in pipe flow. Energy losses in the pipe flow. When the fluid flows through a pipe, the fluid experiences some resistance due to which some energy is lost. Why the fluid will feel the resistance? Because there is a friction exists between the fluid and the pipeline boundary, inside boundary of the pipe, and also there is the various number of obstructions is there. You can see in terms of the fittings, in terms of the bent pipes. So there is some resistance. So because of that, some energy is lost. So while the fluid is flowing through a pipe, fluid experiences some resistance due to which some energy is lost. So this loss of energy is classified as the major and minor losses. Major and minor losses. The major loss is because of the friction in the pipe flow. When pipe is there, then fluid is flowing in the pipe. So this pipe material is there and flow in touch with the pipe material surrounding it. So there is a friction between the fluid and the pipe material. So because of that, energy is lost, and this is because of the friction. That's why it comes under the category of the major loss. So major loss is because of the friction. Here you can see major loss and minor loss. That is, the energy loss is categorized into the two losses, major and minor losses. Major loss is due to the friction, and it can be computed using the Darcy-Weisbach formula, while the minor losses is because of the various reasons like the sudden expansion, sudden contraction, bend in the pipes, pipe fittings, obstruction in the pipeline, also at the entrance and at the exit of the pipe. These are this is the losses in the energy, and these regions comes under the category of the minor losses, and major losses because of the friction. So we will see both. First come to the major head loss. Energy loss, already in the previous session we have discussed about the energy in terms of the energy head, how to represent. Now here we are talking about the major loss and minor loss. This is the major loss. Major loss is because of the friction, in the pipes. It can be computed using the Darcy-Weisbach formula. Fannings also given. Mainly we are using the Darcy-Weisbach formula. We will see both. As per the Darcy-Weisbach equation, this is the head loss due to friction. HF is the energy loss in terms of head due to friction. So that can be written as FLV square upon 2GD. F is the friction factor because of the presence of the friction. L is the length of the pipe. V is the velocity of flow in the pipe, average velocity. G is the acceleration due to gravity, 9.81 in the SI unit, meter per second square, and D is the diameter of the pipe in SI unit. All will be in the SI unit. So you can use this Darcy-Weisbach equation for the computation of the energy head loss due to friction. So while computing how to compute the value of this friction factor, you know the value of the L, length of the pipe, that can be measured. Velocity in the pipe, that also can be measured. Diameter of the pipe also can be measured. G value is constant. So only F is remaining to know. So how to calculate the F? F is the friction factor. Because of the presence of the friction, F is the friction factor. So how to compute the F? For computing the F, first we have to compute the Reynolds number. Reynolds number what is? That is equal to rho Vd upon mu, or we can write Vd upon nu. It is the ratio of the two forces, that is the inertia force to the viscous force. So this Reynolds number formula you can use to find out the Reynolds number. If you know the velocity in the pipe, how much velocity fluid is flowing with the some velocity, if you know the velocity, you know the diameter of the pipe, and you know the kinematic viscosity of the fluid, then we can determine the Reynolds number. So after computing the Reynolds number, we have to see if the Reynolds number is less than 2000, then we can use the formula, this one, that is the F equal to 64 upon Reynolds number. This formula is used only when the Reynolds number is less than 2000. When the Reynolds number is varying from, that is in between 4000 to 10 to power 6, in that case we can use this formula for getting the F value, friction factor value, that is equal to 0.316 divided by Reynolds number to power 1 by 4. So F is called the friction factor, and this is equation is given by the Darcy-Weisbach equation. So that's why F is called the Darcy's friction factor. So this is the way how to compute the, after getting the value of F, you can compute the HF. So using the Darcy-Weisbach equation, you can compute the energy loss in terms of the head due to friction. Now coming to the next one, Fanning's equation. Fanning's equation also given the same equation, likewise not exactly same but the same equation. What is difference? He also used the friction factor, that is F dash. L is the length of the pipe, V is the velocity of fluid in the pipe, G constant value, and R is the hydraulic radius. So Fanning's uses the hydraulic radius instead of the diameter of the pipe. If you see the previous one, Darcy-Weisbach equation, they have used the D, diameter of the pipe, in place of the hydraulic radius. So Fanning's uses the hydraulic radius, that is the difference in the equation. He assumes in the hydraulic radius, whatever the weighted parameter is there, in that only the resistance is there, while the Darcy-Weisbach, they assumes the friction is all over the pipe, not only in the weighted area. So they use the diameter of the pipe, Darcy-Weisbach, while this Fanning's use the hydraulic radius. So this hydraulic radius can be written in terms of the diameter of the pipe. For the circular pipe, R is equal to D by 4 can be written as R is equal to A by P. A is the area, cross-sectional area, that is pi by 4 D square, and weighted perimeter for the pipe, you can write the pi D. So pi D will cancel out and D by 4 will remain. So R equal to D by 4 for the circular pipe. So that we can write here, that is F dash L V square upon 2G D, and 4 will come in the upside. So 4 F dash L V square upon 2G D, this is given by the Fanning's equation. This is called the Fanning's equation, where F dash is the Fanning's friction coefficient, F dash is the friction factor, and that is given by the Fanning's, that's why it is called the F dash is the Fanning's friction factor. Now as per the Fanning's, if the Reynolds number is less than 2000, then you can use the friction factor F dash formula, F dash equal to 16 upon Reynolds number. While Reynolds number value is in between the 4000 to 10 to power 6, you can use the F dash equal to 0.079 divided by the Reynolds number to power 1 by 4. That is the Fanning's equation. So as per the Fanning's equation also, you can compute the head loss due to friction. In this F dash, how to compute the F dash? They have given the formula, that is based on the Reynolds number. So first you have to compute the Reynolds number, then as per the Reynolds number value, we can compute the friction factor given by the Fanning's. So in this way we can compute the head loss in case of the Fanning's equation. If you equate both the equations, then you will get this is the relationship for the circular pipe, F dash equal to F by 4 or F equal to 4 F dash. Simply just we have to equate both the equation, you will get this relationship. Now coming to the minor losses. Minor losses is because of the various reasons, like the head loss at the entrance of the pipe, when the fluid enters into the pipe, then at the entrance there is the loss of the energy, that is called the head loss at the entrance of the pipe, and this comes under the category of the minor head loss. Head loss due to the sudden enlargement, head loss due to sudden contraction, head loss due to some obstructions present in the pipe, head loss due to bend in the pipe, head loss in the various pipe fittings due to various pipe fittings present in the pipe, head loss at the exit of the pipe. When the fluid exit from the pipe, then there is also the loss of energy. So that is comes under the category of the minor losses. So these are the category which comes under the minor losses. Head loss at the entrance of the pipe, head loss due to sudden enlargement, due to sudden contraction, due to obstruction in the pipe, due to bends present in the pipe, at the various pipe fittings, and at the exit of the pipe. So one by one we will see. Here some diagrams is there, you can see. At the entrance there is the loss, and at the exit also there is a loss of the energy. So this comes under the category of the minor losses. Presence of the valves also make the energy loss. Here you can see the gradual change, gradual expansion, while here the gradual contraction. So here diameter is this much, then it is increased, so it is gradual expansion. Here is the gradual contraction. This is the diameter of the pipe, now diameter becomes less, so this is the contraction, gradual contraction. This is the sudden expansion. Here diameter is this, and suddenly it expands to this diameter. Here is a sudden contraction. This is the this much of the diameter is there, then it is suddenly contracted to this diameter. So sudden expansion, sudden contraction. Here gradual expansion, gradual contraction. Bend in the pipe. There is a change in the shape of the pipe, then also there is a loss of the energy. Other fittings are there, like the T-shape fittings are there. So if there is a change in the shape of the pipe because of the any reasons, then there is a loss of the energy, and these are comes under the category of the minor losses. At the entrance of the pipe, head loss can be written as 0.5 v square upon 2g, where v is the velocity in the pipe flow at the entrance. So using this formula we can compute the head loss at the entrance. Head loss due to sudden enlargement. Diameter of the pipe is this much, and here the diameter of the pipe is becomes this much. So there is a sudden enlargement, expansion of the pipeline. So here is the change in the shape of the pipe. So there is a loss of the energy. How much energy will be lost? So this is comes under the category of the sudden enlargement, and the equation is given by this H equal to V1 minus V2 whole square upon 2g, where V1 is the velocity before the expansion, and after the expansion velocity is V2. So using this equation you can compute the head loss due to sudden enlargement. Head loss due to sudden contraction is given by the SC, that is equal to 0.5 into V2 square upon 2g. V2 is the velocity that is after the contraction. Head loss due to the bend, it is given by the HB, that is equal to K into V square upon 2g, where K is the coefficient of the bend. It depends on the coefficient of the bend, and it is K is multiplied by the V square upon 2g. V is the velocity in the pipe flow. Head loss due to presence of the some obstruction in the pipe. This is the obstruction which is present in the pipe. So thus head loss is given by H naught, that is equal to V square upon 2g. This is multiplied by the A upon CC, A minus 1 whole square. So here what is V is the velocity of the fluid flowing in the pipe. V is the velocity which is flowing in the pipe. This A, capital A, one is the capital A, one is the small a, one is the capital A, one is the small a. Capital is the area of the pipe. Capital is the area of the pipeline, cross-sectional area of the pipe. While small a is the maximum area of the obstruction. This obstruction is there, so maximum cross-sectional area of the obstruction is the small a. And Cc is the coefficient of contraction. And Cc is the coefficient of contraction. we will see the coefficient of contraction how to compute. Just so based on this equation we can compute the head loss due to presence of the obstruction. One term is the vena contracta. Vena contracta. Before coming to this one, let's see one more thing. Let me see. That is the coefficient of contraction. This is the ratio of the vena contracta to the actual area. That is the coefficient of contraction. We have used this coefficient of contraction in case of the presence of the obstruction. So vena contracta, let's see now. Vena contracta is the point in the fluid stream where the diameter of the stream is least. This is the important. Diameter of the stream is least and the fluid velocity is maximum. If diameter is least, then the velocity will be maximum. If diameter is more, velocity will be less. So if the diameter is less, velocity will be more, and when the diameter is least, then the velocity will be maximum. So it can be defined as the section in the fluid stream where the cross section of the stream becomes minimum. So at vena contracta, velocity of the fluid is maximum. At vena contracta, this is the section where the velocity is maximum and the pressure is minimum. If the fluid, that is the fluid velocity is maximum, then the pressure will be minimum. This is as per the conservation of our Bernoulli's equation also. We can see that one. So that is the vena contracta. This is exist at the section where the velocity is maximum or stream is having the minimum diameter. Let's see. This is the pipe flow. Flow is flowing in the pipe. Here the change in the pipe diameter. Diameter is this much, then sudden contraction of the diameter. So here change in the shape of the pipe. We can see here the flow is coming like this. Then it is going to be fully occupied the here pipe. So you can see here least diameter is there for the stream. Here the least diameter is for the stream. So here least diameter is there. So here the velocity will be maximum. Stream velocity will be maximum at this section. Velocity will be maximum because of the least stream diameter. So this is called the vena contracta. This section is called the vena contracta section. So you can see also here the graph is given. Pressure is here, the velocity diameter is high or more, so velocity will be low. So velocity will be low, pressure will be high. So pressure is high here. You can see pressure is at this section pressure is minimum, then again it is going to increase. While the velocity is low, opposite to pressure, and velocity is going to be maximum at this section, maximum velocity, then it is going to be decrease. So this is the vena contracta. This is shown in the orifice meter. In the orifice meter, fluid is passing through the orifice meter. So here the stream is going through like this. So that is, stream diameter becomes minimum here at this section. So velocity will be maximum at this section. This section is called the vena contracta. So vena contracta, where the diameter is least and velocity of the fluid is maximum. So this diameter of the vena contracta is slightly less than the diameter of the orifice. We have seen the vena contracta. Now the ratio of the area of the vena contracta. You know the vena contracta, where is the minimum stream diameter is there. So area of the vena contracta to the actual area of the orifice, the ratio of these two is called the coefficient of contraction. So this is coefficient of contraction can be written as AC upon A naught, where AC is the cross sectional area where the vena contracta exists, and A naught is the orifice area. So this is the coefficient of contraction. This is the coefficient of coefficient of contraction. So in case of the orifice, Cc value, the coefficient of contraction is 0.64. So smaller the value of the coefficient of contraction, Cc value is, then more the effect of vena contracta will be there. If value is high, then vena contracta value, if the value is high, this coefficient of contraction is high, then this vena contracta effect will be less. Its effect will be more when Cc value is less. From this formula also you can see that is the vena contracta. So this is used in the design of the flow meters like the nozzles, orifices, mouthpieces. Now the head loss due to the various pipe fittings. Pipe fittings may be the adapter, maybe the barb, maybe the elbow, maybe the toe, cross type, maybe the nipple, maybe the union, maybe the valves. So various pipe fittings are there. So because of that, head loss is given by as the HV equal to K into V square upon 2G. HV is the head loss due to various pipe fitting, that is equal to K into V square upon 2G. K is the coefficient of pipe fitting and V is the fluid flow velocity in the pipe. Head loss at the exit of the pipe. At the exit of the pipe, head loss is equal to V square upon 2G. H naught is the head loss at the exit of the pipe. When the fluid is exits from the pipe, also there is a change in the cross section. So here that is the change in the shape. You can say at the exit, here the something change is filling. If some change is there, there is the loss of the energy. Here change is there, so loss is there. So at the exit, loss is H naught, head loss, that is equal to V square upon 2G. V is the fluid velocity in the pipe, G is the acceleration due to gravity. Using this formula, you can find out the head loss at the exit of the pipe. So this is about the major and minor losses when the fluid is flowing through the pipe. For this session, thank you.